the last class, we had discussed features of DSP processors, and we had looked at one of the DSP processors from TI, that is C54X and that family. Today, we shall look at some more DSP processors and their architectures. The first processor that we are looking at, it is again from TI, and this is typically 55X architecture. This is a power efficient DSP processor which is really targeted for personal and portable applications like your cellular phone. And here the basic difference with the earlier architecture is to improve the efficiency with parallelism in instruction execution. And another feature is automatic power management mode, which is in much more elaborate fashion than what we had found earlier. Architecturally, you will find here that the MAC unit is now, there are now two MAC units, that is, it has been duplicated, and it has got the same 40-bit ALU, but additionally there is a 16-bit ALU for optimizing parallel operations. It supports 12 internal buses to perform up to 3 data reads and 2 data writes in a single cycle. And you can understand these architectural modification has been done to increase data throughput and consequently the output, that is the result that is being generated, the rate at which the result can be generated, that also can be increased. In terms of the architecture overview, you will find that this processor supports variable length instructions. The advantage is that you can have better code density. It uses software stack and not a hardware stack, so that you can do a 32-bit push and pop. The CPU, the basic core processing unit, is divided into 4 subunits: instruction buffer unit, program flow unit, address data flow unit, and data computation unit. These units facilitates multi-stage pipeline implementation, which again increases throughput. This is the basic diagram of the CPU core. We have not shown the basic components, but primarily the computational elements here. So you'll find that it has got two 17x17 MAC units, that is multiplier, adder, as well as rounding and saturation hardware. It has got a 40-bit compare and select unit. Then it has got 4 accumulators. So obviously I can accumulate more results. Also we have got a barrel shifter. It's a 40-bit barrel shifter. Along with it, you will find you have got a 16-bit ALU. Apart from the regular ALU, it has got the 16-bit ALU, which is primarily used for address calculations. There are data and auxiliary registers, and you will find a block which is dedicated for the power management. These are the buses, data read, data write buses. This is a program bus which is separated out, and this is a peripheral bus for connecting it to peripherals. So instruction buffer performs what we call 32-bit program fetches and stores instructions for program flow unit. So obviously it is responsible for implementation of what we call prefetch in a pipeline stage. The program flow unit decodes and directs address data flow unit and data computation unit, which comes subsequent to program data flow unit. In fact, program fetches are performed using 24-bit program read address bus. So addresses of 24-bit and what you get the words, that is your instructions, in chunks of 32 bits. And functional units read data from memory or I/O space. These are functional units, means these are basically your either MAC units. Continuous data read on these buses. There are two 16-bit data write buses. So, these buses are exclusively meant for writing operations. So, all these operations can be actually overlapped in time, that is program read, data read and data write, and that too on multiple data read and write buses. So, the organization is something like this. You have got an instruction unit, program flow unit, address unit, data unit. So, when you read an instruction, this instruction word, which is a 32 bit, that means instructions are fetched in packets of 32 bits, they come to instruction unit, and the address is provided on the program address bus. Next, you will be reading the data, okay, depending on the instruction being executed. There are 3 data read buses, each of which is 16-bit width, and these are the data read address buses. In fact, you will find various combinations of data reads and usage of buses for that purpose. So, when you are using a single operand read, you will be using what is called a D bus inside the CPU. Dual operand read, 2 buses, C and D buses, and dual multiply coefficients, that is, you are trying to do 2 multiplications simultaneously using the same coefficient, then the data, that is a common coefficient, will come along the B bus. You will be writing data via the write buses and write address buses, and these buses, what I have shown is primarily the internal buses, and these buses will be interfaced to the external world, that is your external memory, by a special unit which is called external memory interface unit. So, as I have already stated, that instruction buffer unit fetches 32 bit packets from memory. Instruction buffer queue size is typically of 64 bytes. That means that many instruction bytes can be buffered and stored. It decodes 1 to 6 bytes of code using the instruction decoder. Once it decodes, it passes the data to PU, AU and DU for execution of the instructions depending on the instruction that has been actually fetched. Instruction buffer queue has a very important role to play, is that of implementation of a block repeat instruction. That means when I am doing a block repeat, that means I am repeating a sequence of instructions. And where is these instructions stored? They can be stored in the instruction buffer unit. So, what the processor does, it executes a sequence of instructions which is stored in the buffer. The program flow unit receives instructions from IU, generates all program space addresses and also controls the sequence of instructions. That is, it interprets the conditions for conditional instructions, because here also you will find, as in ARM, there are conditional instructions to increase the code density and to have an efficient utilization of a pipeline, and it also determines the go to addresses. It initiates interrupt servicing, manages single repeat and block repeat operations, and manages execution of parallel instructions. In fact, this DSP has a facility to have parallel instructions. We shall come to that point when you look at the instruction set. So, what you find, that program flow unit actually controls execution of the instruction. So, if I take the simple example of a kind of a block repeat, that block repeat management is done by PU, but the instructions are in the buffer. Okay. So, this unit manages the exact control flow of the program that is being executed. Address data flow unit, which is actually AU, contains the logic for generation of addresses. It uses a set of registers, because actually you will find that since you are having multiple data buses, you can actually get multiple operands and you need to generate addresses for these multiple operands. So, that is why address data flow unit becomes a very important component for a DSP architecture. It uses a separate 16-bit ALU, and this ALU is different from that ALU which is being used for actual computations. Okay? And it includes 4 general purpose temporal registers, and simpler operations can be executed in parallel with that of DU. That means you can realize that since there is a 16-bit ALU here, I can execute an instruction on the 16-bit ALU in parallel with actually an instruction being executed on the data unit. So, data unit basically consists of the 40-bit ALU with the 40-bit barrel shifter that I had already shown, 2 MAC units as well as 4 40-bit accumulators. And it can perform 2 arithmetic operations simultaneously when a dual 16-bit instruction is executed. In fact, you can understand this pretty well, that since you have got 2 MAC units, obviously I can execute 2 multiplication operations in parallel. Also, with those multiplication operations, you can execute an arithmetic instruction on the 16-bit ALU, which is part of address data flow unit. This pipeline, since we have got so many units, obviously it facilitates implementation of a multi-stage pipeline. In fact, we shall not go into the details of these stages, but we can say that the basic pipeline is divided into 2 phases: fetch and execute. And in fact, these 4 and 7 to 8, these numbers indicate number of sub stages in each of these pipeline. So, it is a pretty extensive pipeline, and the whole purpose is to increase the throughput. That means when we have the pipeline full and we are not having any problems related to pipeline flush, the instruction execution can be pretty fast. The other feature of this pipeline is it is what is called a protected pipeline. It introduces inactive cycles between instructions that would cause conflicts, like reading and writing from the same location out of the intended order. Okay? So, that means when there are 2 instructions in the pipeline ready to be executed and they are accessing the same location, and maybe one operand of an instruction is dependent upon computation done by the previous instruction, then obviously I cannot do a operand fetch till my instruction is executed completely. So, in that case a pipeline stage has to idle. So, I need to have inactive cycles. So, that is automatically introduced for efficient pipeline management. The memory space is interesting in case of C55X. Although it has got a separate data buses, program buses, that is address as well as program data bus, it can consider its memory as an unified program data space and separated IO space. In fact, it has got separate IO address space, separate program and data space. So, in fact, that all 16 megabytes of memory is addressable as program space or data space. So, it is a kind of a modified Harvard architecture. It is not classical Harvard architecture such that your address space and data space is absolutely distinct, and it can even have different sized words. Okay. So, here the whole memory space can be addressed together as a program space as well as data space. So, it is a modified Harvard. CPU reads instructions from memory that uses program space addresses, and data space consists of what we call the general purpose memory and MMRs. What are MMRs? MMRs are memory mapped registers. That means we are not talking about a separate set of registers for doing data processing operations. We are referring to a set of memory locations, and these are on-chip memory locations which we are considering as memory mapped registers. In fact, you will find here similarity with the concept of PIC registers. The PIC registers was part of the memory itself. The register bank itself is the RAM for PIC. So, here there is a register memory map registers as well as general registers. So, CPU reads instructions using what we call 24-bit addresses. You have found that all address buses are of 24 bits. So, addressing capability is 2 to the power 24. So, CPU reads instructions using 24-bit addresses that are assigned to individual bytes. So, therefore, this is again a byte addressable processor. Data accesses are interesting because it accesses 16 bits at one go, okay, and so effective address is 23 bits. And the whole data space is divided into 128 data pages, and each data page has got 64k words. And on data page 0, the first 96 words are reserved for what are called memory mapped registers, okay. Now, this whole memory that we are talking about with the addressing capability of 2 to the power 24 is not necessarily resident on the chip. Some part of it is on chip and some part will be external. Now, let us look at an instruction sets. We shall not look at the basic instructions because there is a distinct similarity of these instructions with the other processors that we have looked at. It has also got some special instructions which are targeted for signal processing applications, okay. But very interesting thing apart from all these is the concept of parallel instructions. We have not come across these parallel instructions so far in the architectures that we have discussed. So, what are parallel instructions? Here you can actually write a single instruction which is part of your instruction set, which results in execution of 2 instructions in a single execution cycle, okay. Now, when it is part of the instruction set of the processor, we indicate such instructions as built-in instructions. There is also a provision for the user to indicate such parallel instructions. So, they are user defined, and you can even combine system defined parallel instructions with additional instructions specified by the user and intended for parallel execution, and that is what we refer to as combined form of parallel instructions. So, this is a feature which is unique to C55 among the processors that we have so far discussed. Obviously, you can understand the whole motivation is to make use of additional hardware, increase the rate at which your data stream can be processed, input data stream can be processed. In the addressing mode, we are looking at in particular the addressing mode which is used for these parallel instructions. In fact, it uses indirect addressing. In fact, the registers which are available for address purpose, they are address store purpose, they are used in many cases for these address generations. So, you have got indirect addressing where and this AR indirect addressing is typically used when you are accessing 2 memory words. These 2 memory words will be required for general instructions as well as when you are executing 2 instructions in parallel, because if you are having the operands are in memory. So, you need to access these operands, 2 operands for 2 instructions. So, you use typically an indirect addressing mode, and this indirect addressing mode is dual indirect addressing modes. There is other general addressing modes are also available with this processor which are commonly available, but this dual indirect addressing mode is another distinctive feature of this processor. Other interesting thing is coefficient indirect addressing mode. Here this instruction is actually part of the instruction set of the C55. You can understand this is a dual multiply instruction, and this is a symbol in the assembly language of C55 which indicates a built-in parallel instruction. Here this data, that is X memory, is actually being multiplied by a coefficient which is stored in this CMEM, and the result is going to accumulator X. This is again being multiplied and the result is going to accumulator Y. So, two multiplications to be performed in parallel, okay. And this operand, you will find this one is common to both the multiplications. So, you can realize the utility of having 3 buses. Since you have got 3 buses and this data is common between the 2 operations. So, using the 3 buses, I can actually execute 2 multiplications in parallel. So, typically the instruction examples are something like this. Here what we are doing? We are actually referring to, this is star is a standard pointer convention. This is again a convention which used in the assembly language of C55. We are pointing to memory locations, okay. And you can find out that these are, through this register I am pointing to memory locations, 2 distinct memory locations, and this is a common memory location which has got the coefficient value. So, if you consider the same coefficient value being used for 2 multiplications x and y, I can use that and do 2 multiplications in parallel and exploiting dual MAC. The user can also define these parallel instructions. If you look here, this is an example where user has indicated an XOR operation, and this is a 16-bit operation, okay. And these instructions, the first instruction is executed by the data unit and second instruction is in AU, which has got the 16-bit ALU, okay. Now, therefore, you will find that user has got now flexibility of specifying parallel instructions, that is multiple instructions being executed in parallel. Obviously, these instructions, if they are to be executed in parallel, certain rules and conditions have to be satisfied. One condition is that the parallel instruction does not exceed 6 bytes. Why this 6 byte restriction is coming in? From the instruction buffer, because it actually provides the 6 bytes and decodes it. So, both the instructions should be decoded at the same time and decodable in the instruction unit, so that you know that they can be executed in parallel. Further, there should not be any hardware resource conflict. If there is a hardware resource conflict, then obviously 2 instructions cannot be executed in parallel. And you have got the facility of combination. What is combination? So, this is an built-in instruction. So, with this built-in instruction, you can even specify a 16-bit operation. So, you can have got 2 multiplication plus a 16-bit operation which can take place in parallel. Now, let us come to on-chip memory and peripherals. I was referring to the memory access and data access. Now, which part is in on chip and which part can go outside? In fact, on chip memory you will find this is 32K ROM, which is typically expected to be your program memory. You have got 256K single access memory and 64K dual access memory, okay. So, these dual access and single access are required because you are doing what? You may do a simultaneous read and write onto the memory. So, in that case the dual access is important. You have got the timers, serial ports, 8 general purpose digital IO pins, which is typical to a particular version. It can change from chip to chip because I am just representing the generic configuration. And interesting thing is it has got an enhanced 16-bit enhanced port interface. It has got EMIF. Now, this is for doing 16-bit interfacing with devices, IO devices, and this is for interfacing memory, external memory. Apart from it, you have got a DMA controller, and these are some special purpose serial ports with buffering capabilities. It also provides for what is called configurable instruction cache, okay, which is where if you have the instructions, the access is faster and you can increase the data processing efficiency. So, this is the basic block diagram. Other than we have so far discussed the CPU part of it. Apart from CPU, on the chip itself there are other peripherals. So, what you can see is this is my DMA controller which is connected by a peripheral bus controller. If you remember the first diagram, I had showed a peripheral bus. So, peripheral bus controller controls a peripheral bus, and on the peripheral bus is actually all these timers, serial ports, all these sits on the peripheral bus. And this is your DMA controller, and DMA controller has itself a DMA bus which is this interface to the external world through this enhanced host bus interface, and these are basically memory blocks. This is the ROM, this is single access RAM, this is basically dual access RAM, and through this external memory interface block you can connect to external memory, and CPU buses are therefore connected to this external memory interface if when it is accessing external memory as well as to the internal memory locations. Now, EMIF is actually the block which decides on the interface issue. Now, so interface is configured by the CPU and it is a hardware which services data transfer requests from 3 internal resources, that is program fetches from the CPU, data accesses from the CPU and data accesses from the on-chip DMA controller. And in fact, the whole idea here is that there is a specialized hardware which enables you, the chip, to interface to different external memory devices. Because these devices can have different timing constraints, they can store words, that means their inherent storage can be of different bit lengths. It may be an 8-bit memory, it may be a 16-bit memory. So, all these interface issues are being managed by a separate controller, and that is exactly what is EMIF. So, CPU is not really concerned with this management task of interfacing with external memory devices. Similarly, you have got EHPI, which is a 16-bit wide parallel port through which a host processor can directly access DSP's memory space. Now, this is an interesting feature. Why? Because there can be a general purpose host which can use DSP as a coprocessor. So, I need to provide a general purpose external host some access to DSP. So, this EHPI provides that interface. Okay. So, this can be connected to an external host. In fact, it can be connected to other peripherals also if required. Okay. Now, EHPI communicates with memory, that is, it provides communication with memory. If you remember the block diagram, the DMA controller was connected to this via dedicated auxiliary DMA channel and internal DMA buses that provide connectivity to the entire DSP's internal memory and part of DSP's external memory. So, what is the significance of this? Significance is that external host, it may be a processor, it may be a codec also, can transfer the data, okay, onto the DSP's memory for processing. Even a CPU can influence what the code the DSP executes. It may even generate and write the code in the DSP's memory that DSP is expected to execute depending on the task which is being given to the host for execution. These are serial ports, and this is these serial ports are typically buffered serial ports, and these are special serial ports you will find in many of the DSPs, okay, not only on these but other DSPs as well, designed to interface to devices such as other DSP processors. It has got a specific form. It is double buffered transmission and triple buffered reception. So, you can understand the buffering means there can be the timing synchronizations with the external device can be done by the DSP using the buffers. Okay. So, it can be full duplet, double buffer transmission, triple buffered reception. It works with interrupts or DMA and it is highly programmable. In fact, if you look at the basic block diagram, if you see that you can program it for register for synchronization control, sync control, since it is a serial transmission, so I can do a sync control and monitoring. Registers for multi-channel control and monitoring, and I can specify the clock and frame synchronization, because this is a clock signal. Because of a serial synchronized transfer, I need to have a clock. So these are the lines for data receive or transmit, and it is buffered. So it can also actually raise an interrupt request or a DMA request for a data transfer. Okay. So this provides you with a serial interface with external devices, which can be even another DSP. Next, we look at power management. In fact, we have remembered that there is a dedicated power management block. Now, how does really the power management comes into play? You have found that C55 has got various functional blocks. It is not that for all tasks, all functional blocks are required. So, what has been done is the designers have got 6 software programmable power domains on the processor. They are CPU, DMA, peripheral clock generator, instruction cache, external memory interface. And each domain can be put to low power idle mode when its capabilities are not required. Okay, and this is completely under user control, that is software control. User even define ideal domains. So with these ideal domains, it can put some parts in ideal mode and reduce the power consumption, depending on whether the task requires these features or interfaces or not. Take for example, when I know in my software I shall not be accessing the external memory, I can definitely put external memory interface in idle state and save power. So if you remember, I started with saying that C55 is targeted for a power efficient DSP architecture, and this is one of the manifestations of these, that facility to define idle domains and can put the different on chip blocks to idle mode under software control. Now, if we compare C54 with 55, what we have found is enhancement in the architecture primarily to increase the rate at which data can be processed. But still this is a fixed point architecture, and a very distinct thing that you have observed here is ability to execute multiple instructions in parallel because of the additional hardware. Now we shall look into some variants of this DSP architecture where this feature has been explored in full. We have already come across assigned instructions. Okay. Now assigned instructions are basically meant for multimedia data types. In fact, the example that I had started with, say, image sensor, and from each side I can get a 8-bit data, and if I am doing any kind of image processing operation, I shall be operating on each and every pixel. So I shall be operating on 256 on 256 cross 256 pixels if my image size is 0 to 255, okay, by 0 to 255, that means a squared image. So if that many operations are to be performed, and these are same operations and repeated operations. Similar thing is true even for audio signals. You are taking samples at regular intervals, and similar operation will be performed on each and every sample. So there is a motivation for what we call SIMD instructions, that is single instruction, multiple data. In fact, we have seen this in the context of ARM version 6 architecture as well. So effectively what we are telling is, if I have really 32-bit or 64-bit registers with the processor, I can logically divide these processors into say 4 words. In this case I have done for a 64-bit, and I have done an addition, and here the addition is word wise addition, okay. And what we say that 4 additions per instructions, and carry is disable at word boundaries. We can even have a saturation mode, and that effectively is doing what? Reducing the number of instructions actually need to be stored as well. So, you can realize that code density also increases. So, in fact, this assembly instructions for this kind of multimedia processing is today common not only for embedded processors, but also for general purpose processors as well. Here we have given some examples. HP Precision architecture is an old architecture, one of the earlier architectures which implemented this. This Pentium MMX, okay, which is coming with all of your pieces, they have got 64-bit vectors representing 8-byte encoded or 4-word encoded or 2 double-word encoded numbers. That means you can have these kind of combinations of arithmetic instructions. You can have 8-byte encoded in 64-bit. So, if you are doing an add, in that case you have 8 additions taking place in one instruction cycle. Similarly, if you have 2 double word, then maybe 2 double word additions in one instruction cycles. UltraSPARC has got an instruction set which is visual instruction set. In fact, there the instruction set, one of the features of this instruction set is this has been optimized for processing of the video data. Because you will find that today if you are getting your cameras or even your cell phones ability to capture video, encode video, that is compressed video, store, send, etc., then I need first hardware to do video compression. In fact, the first such feature, this is not for really embedded system, this was done on the workstation level, but they introduced special instruction sets which had assembly instructions to facilitate video processing. And ARM version 6 actually that we had discussed in one of the previous classes makes use of these assembly instructions for these kind of signal processing tasks for embedded domain. Now, a next thing is what is called very long instruction word processors or VLIW processors. Here I have got parallel operations encoded in one long word, each instruction controlling one functional unit. So, we say that this is an instruction packet, this is an instruction 1, this is an instruction 2, this is instruction 3 and this is instruction 4, all part of a single instruction packet, and they are activating different functional units in parallel. And in fact, this is exactly the extension or enhancement of that feature that we have found in C55. Okay? But in C55 it was not an explicit VLIW instructions, but when we have a VLIW processors explicitly with the multiple units, I can have these kind of long instruction words in which multiple instructions can be specified for execution in parallel. So, in this case what happens? If we consider this, then we need a large register file which would feed multiple function units. Okay. So, if we take an example, let us say I have got these instructions, okay, a very large instruction word architecture. In this case, an instruction packet will have opcodes for say addition, register additions, subtractions, a load, a store, a NOP. The interesting feature is you obviously have seen here, just like I was talking about parallel instructions, there should not be any hardware resource conflict. That means the registers that we are using are different. Therefore, these instructions which are to be executed, they should feed into the ALU the data from the corresponding register file. So, effectively this instruction and the data from these registers would go into here and the result should be stored back Similarly true for subtraction. And interestingly here I have shown even other than ALU or arithmetic units, I have got load store units. These load store units taking care of load and store requirements. Now, register, the other option, the organizational option for VLIW architecture is that instead of having a single register file feeding into all the functional units, you can have register file and function units divided into what are called clusters. And there is a common cluster bus, and from there you feed into the execution units, and each execution unit is associated with its own dedicated set of register files, which is used for doing computation using multiple functional units. Similar to that cluster concept is this implementation which is in TI C60X family. We have looked at C55X family, now we are looking at a 60X family, which is actually an explicit VLIW processor. Okay, the whole architecture is motivated on VLIW processor, and you will find that in this case obviously the many memory ports are required to supply enough operands per cycle. So, what is being done here is that whole data path, okay, you have got its feeds into the two register bank set, register file A and register file B, and they feed into these functional units. Okay. So, these are address buses if they are generating the address units, and these are the data buses which are feeding onto the register files, because if I am getting a data from the memory or one register file to another register file, I need to have a data bus connecting them together. Okay. And these are the functional units which are connected directly to two different register files. So, this is the basic organization of 60X family of TI processors, which are VLIW digital signal processors. So, we are looking at 62, 67, some examples of these processors. They can execute up to 8 instructions in parallel per cycle. Okay. Obviously, you will find this is definitely an enhancement over your C55. It has got 32-bit registers, and these are the functional units, that is 2 multipliers and 6 ALUs, and all instructions execute conditionally. So, obviously, if some instructions need not be executed, that may be part of a long instruction word, and that function units is not used. So, executes what we call an inactive cycle. So, it has got 8, 16 and 32-bit arithmetic as well as 40-bit operations. It also has got bit manipulation operations, so variety of operations which are available. So, obviously, you can find that ability to process so many arithmetic operations in parallel increases its capability to handling huge volume of data, and that is exactly the motivation, that when we are looking at this media data particularly, it is not just the data coming from a pressure sensor or a proximity sensor, but really media sensors like image and speech audio, you really get high volume data, and you need to do a substantial amount of processing on this data for doing compression and decompression, basic tasks, and therefore, these kind of processors are targeted for these applications. In fact, just like your C55X family, C6X family has got on chip RAM, it can have 32-bit external memory, it has also got a host port, multiple serial ports, multi-channel DMA, 32-bit timer. Okay. These are standard peripheral blocks which you expect on many of the other processors as well. So, this is the basic idea of what a basic organization block diagram. So, it has got a program RAM or cache, data RAM or cache, the same bus. It has got a DMA controller, and there are 2 data paths. Okay. Along these data paths, there are 2 register file banks which feed into the execution units. This is 67x processor architecture. The reason why I have shown this diagram is you will find that these many internal buses have been provided. Okay. This is on chip memory and this is your DMA controller. Okay. This is just the same an exact implementation of the previous generic architecture diagram that I had shown. And these are the basic functional units D1, M1, L1 and S1. So, these are the basic functional units. It has got the register file A and register file B feeding into these two functional units independently, and the program control unit knows how these functional units have to be used. And these are the data paths. Now, interestingly you will find that it has got the data paths, 32-bit is a DMA data bus and these are 64-bit data buses. Even program data bus is a 256-bit. Obviously, why? Because it is a VLIW processor and its instruction size would be large. That is why the program data bus has to be 256 bits. And this is a very basic feature of any of the VLIW processors. So, as we have seen in the data path that you have got general purpose register files, 8 function units, 2 load units, 2 store units, 2 register file cross paths and 2 data address paths. Okay. So, let us look at what are these functional units really doing. Now, among various tasks, I am just representing some of the basic tasks. This L represents basically 32 or 40-bit arithmetic. It can do logical operations, it can count the leftmost one counting. S is also doing 32-bit arithmetic and 40-bit shift, and it can do branches. So, this shifting is what is distinguishes S from L blocks. M is basically the multiply units, and D is the address, basically manages address as well as load store. And so, if you remember in the basic block diagram and the organization diagram, I showed why the D block is connected to the address bus. Okay. So, it will do 32-bit add, subtract, circular address management, etc. Now, similar to C6X, the SHARC processor, SHARC is again another DSP, this is coming from different manufacturer, which also implements Harvard architecture. It implements the memory divided into 2 blocks, PM and DM. But the most important feature of SHARC is it's a floating point DSP processor. So, it has got a floating point arithmetic unit inside and it has got floating point instructions. The functional units are basically ALU, multiplier as well as shifter. And it is a more RISC like processor. Okay. So, it implements a load store architecture. It has got 2 data address generators for the program memory and for the data memory. Okay. Just like any other processor, it also implements special loop instruction and 0 overhead, but let us look at SHARC for implementation of this special loop instruction, because this gives a particular case study how it can be implemented. So, you have got a loop counter stack for nested loops. Okay. So, if I have a loop counter and there are nested loops, what does that mean? The inside loop has to be first finished before I go into the outside loop. So, the loop counts have to be put into stack, okay, so that in hardware I can keep track of the nested loop, because it is not happening in software. In the hardware itself, by a single instruction you are telling that following sequence of instructions have to be executed a fixed number of times, and that set of instructions can have loops in itself. Okay. So, I need to have a stack of loop counters. So, this is a hardware stack which is made available for implementation of nested loops. Also, it has got a PC stack. In fact, we talked about the TI 55 where we said it is a software stack implemented in the memory, but SHARC has got a PC stack. It is 30 deep for storing subroutine return as well as loop addresses. I hope you understand why loop addresses. The beginning of the loop, where we come back to the loop, that has to be stored in the form of a stack in the PC. So, this gives a particular implementation scheme in a DSP for loop, zero overhead loop, as well as the subroutine call. And this is what I wanted to discuss distinctly for SHARP. SHARP is a VLIW processor, and it implements a number of instructions in parallel. And here you can have various combinations. You can have fixed point as well as floating point combinations. Obviously, you can realize the internal hardware for SHA could be more complex because it is supporting floating point operations. And as I have already discussed earlier, that floating point operation implies what? Additional power consumption as well. There is another processor which we like to look at is Philips TM, because this is a processor which has been used widely for multimedia processing, and this is again a VLIW processor, but there are some distinct features for it. It supports floating point operations just like your SHARC, and it also has some more customized operations for these media processing tasks. In fact, it is a much more elaborate in terms of hardware architectures, and it is particularly intended for media processing. So, if you look at the architecture, you will find this is, I have got a VLIW CPU, but along with VLIW CPU, there are specific coprocessors. In fact, this is also a trend for various dedicated DSPs which are getting designed. So, these coprocessor is particularly for image processing, and this is also for various VLD coprocessor. This is also variable length coding applications like say Huffman coding application. This can be used for implementation of Huffman coding, and it has got specific peripheral blocks for enabling video in, video out, audio in and audio out, and apart from the expected memory interface which is common with other DSPs as well. So, this is an example of a trimedia. This is the Philips media processor, that when we are designing a DSP for a particular task, your choice of interfacing blocks can become different. So, in this case you have got the interfacing blocks which are targeted for video and audio, and you may also have coprocessors. We had discussed the concept of coprocessors with ARM, and we looked at there may be special instructions in the ARM family itself which has the instructions targeted for coprocessors. Here we have seen that in the same silicon area itself, we are talking about an image coprocessor as well as variable another coprocessor which can be used for this coding and variable length compression tasks, and the basic VLIW CPU is this. And this VLIW CPU has got an interesting organization also. So far what we have looked at, we have looked at the same register file, okay, or partition register file. Now here there is a single register file, but there is a cross bus switch. Just like any kind of a communication system, we have a cross bus switch for connecting these functional units to registers. There is a switch here. Depending on the instruction, the switch gets programmed. So, effectively I can establish a path from a particular register to a particular functional unit, and you will find that the number of functional units here it is of the order of 27. Okay, so, since we are having a large number of functional units here, so I really cannot have register files separated and provided separately because there may be different demands. So, there is a cross bus switch which is providing this kind of a communication. So, this finishes our discussions on DSPs. We have studied primarily the architectures, some features of their instruction set. We have looked at VLIW, and we know that why VLIW is a kind of a preferred architecture, because there has to be a number of instructions. A number of instructions can be executed at different data items, and that's the VLIW architecture is being adopted in a variety of processors which are getting implemented. But one issue that I have not discussed is that how to generate the combination of instructions which are to be executed in parallel. If I take a simple example of C55, if you are doing an assembly language programming, you may put instructions in parallel explicitly and then check whether there is any kind of a resource conflict after assembling and running on it on a simulator, but that becomes a complex manual process. So, today's compilers which are targeted for these processes, they are provided with some of the spatial logic to detect these parallel possibilities. That is, from your code itself, whether these parallel possibilities can be extracted and accordingly whether the low level machine instructions can be assembled together to exploit the available hardware to the maximum possible extent. In fact, there are also responsibilities which come to the programmer as well, so that compilers can easily detect these features and generate efficient code. In the next class, we shall look at what we call system on chips, where a processor core and a DSP may sit on the same silicon area itself for a dedicated task. There may be other combinations as well, because the system on chips are becoming very important for embedded systems, because if you get one such system on chip, all the functions can be mapped onto it and the complete system may be built around it. Any questions?
What is it? How is it zero overheads?
Okay, the question is how is it that we are having a zero overhead loop in Sharp architecture? See, the basic idea of a zero overhead is that when you are executing a loop in the software, you actually check that whether you are the number of times. Let us consider that I want to execute these following 3 instructions 5 times. So, I shall have a counter stored in some register, I shall decrement the counter using a specific instruction and check whether it has become 0 or not to terminate that loop. So, there is an instruction overhead. These are overhead instruction for implementation of the loop. But if that entire thing can be built into the hardware, that means I say that following set of instructions to be executed 5 times. So, every time instruction gets executed, this decrement takes place and the check takes place in the same instruction cycle itself. So, effectively you are not having any instruction cycle overhead for implementation of the loop.